The cosmos is full of answers we have not yet learned to question. For every beautiful nebula we photograph, there exists a shadow we cannot explain. This is a countdown through 25 of the universe's most stubborn secrets, phenomena that defy every textbook and challenge the brightest minds on Earth. By the end, you will have a front row seat to the edges of human knowledge, where the greatest puzzles of space and time remain wide open. We will encounter a signal from the void that has never repeated, and a force so strange it is tearing the fabric of reality itself. What part of the unknown universe calls to you the most? That search for a definitive signal began in earnest on one quiet August night in 1977. At Ohio State University's Big Ear radio telescope, a routine sky survey was underway, listening to the static hiss of the cosmos. Then, for exactly 72 seconds, the silence broke. A powerful, narrowband radio burst erupted from the direction of the constellation Sagittarius. It was not the broad, messy static of a natural cosmic event, but a focused, intense signal on one specific frequency, the kind of signal a civilization might use to announce its presence. When astronomer Jerry Amon reviewed the computer printout days later, he saw the alphanumeric code representing the signal's strength, so extraordinary that he circled it in red pen and wrote a single, famous word in the margin: "Wow." The wow signal, as it became known, remains a perfect mystery. It was never heard again, despite decades of dedicated listening toward that same patch of sky. The leading natural explanation points to a comet, but the specific comets proposed were not in that region of space at that exact time. Other ideas, like a passing interstellar asteroid or a strange stellar flare, failed to match the signal's unique, clean profile. It does not fit the pattern of any known cosmic object. This single event stands alone, a one-time shout into the dark that we happen to be listening at precisely the right moment, with precisely the right instrument. For many, it is the closest we have ever come to hearing a hello from another world, a tantalizing whisper that proves the universe is capable of sending messages we do not yet understand. Its enduring power lies in that silence that followed, a question mark hanging in the void for over 45 years, begging for an answer that has never come. While the wow signal was a singular shout from the void, our second phenomenon is a constant, silent scream woven into the fabric of everything. It is the ghost in the cosmic machine, an invisible presence so vast that it outweighs all the stars, planets, and galaxies we can see by a factor of 5 to 1. We call it dark matter, and its evidence is not in what we see, but in what we cannot ignore. The story begins with galaxies themselves. In the 1930s, astronomer Fritz Zwicky noticed something bizarre about a distant cluster of galaxies. The individual galaxies were moving so fast that the visible mass of the cluster, all its shining stars, was not nearly enough gravity to hold them together. The cluster should have flown apart long ago. He called the missing mass dark matter, but the idea was largely shelved for decades. Then, in the 1970s, Vera Rubin provided the definitive proof. By meticulously mapping the rotation of spiral galaxies, she found that stars at the outer edges were orbiting just as fast as those near the center. This defied the laws of gravity as we knew them. Think of our solar system, where distant Pluto plods along slowly compared to Mercury, which races around the Sun. In a galaxy, if all the mass were in the visible stars and gas, the outer stars should crawl. They do not. They whip around as if caught in the grip of an immense, invisible halo of mass, a halo we cannot see. That is our first clue. The second comes from gravity's magnifying glass. Massive objects like galaxy clusters warp the fabric of space-time so profoundly that they bend the light from objects behind them, creating distorted, stretched, and sometimes multiple images of distant galaxies. This effect, called gravitational lensing, allows astronomers to literally map the distribution of mass in a cluster. The maps consistently show far more mass, creating far more warping than the cluster's visible light accounts for. The mass is there, bending light, but it emits none of its own. The final universe-scale evidence is etched into the afterglow of the Big Bang itself, the cosmic microwave background. The precise patterns in this ancient light reveal how matter clumped together in the early universe. Ordinary matter alone, pulled by its own gravity, could not have formed the vast cosmic web of galaxies we see today. The blueprint required a scaffolding of something else, a cold, slow-moving, and invisible form of matter to act as the gravitational anchor for all cosmic structure. So what is this stuff? We know profoundly what it is not. It is not planets, black holes, or cold gas. It does not interact with light at all, no emission, no absorption, no reflection. It is truly dark. It seems to interact with the universe only through gravity, which is why we can feel its pull but not see its face. The leading theoretical candidates are particles born in the fiery first moments of the cosmos. One candidate is the WIMP, or weakly interacting massive particle. As the name suggests, these hypothetical particles would have mass and interact only through the weak nuclear force and gravity, making them incredibly difficult to detect. The other prime candidate is the action, a particle conceived to solve a different puzzle in particle physics, which could also be light, abundant, and behave exactly like dark matter. The hunt for these phantoms is one of science's grandest endeavors. Deep in underground laboratories, shielded from cosmic rays by miles of rock, ultra-sensitive detectors wait for the once-in-a-lifetime tremor that might be a dark matter particle bumping into an atomic nucleus. In powerful particle colliders, scientists try to create dark matter in miniature collisions, searching for an imbalance of energy and momentum that would signal something invisible carrying it away. Every day we move through this silent ocean of dark matter, utterly unaware of its presence, yet it holds the very architecture of the cosmos in its invisible hands. It is the ultimate cosmic sleight of hand, a missing piece so fundamental that without it, our universe, and we within it, would not exist at all. If dark matter is the invisible glue holding galaxies together, dark energy is the phantom force tearing them apart. While dark matter pulls with the relentless grip of gravity, dark energy is the opposite, a repulsive pressure embedded in the very emptiness of space. Its discovery in the late 1990s was a shock that overturned our most fundamental understanding of the cosmos. For decades, scientists believed the universe's expansion, set in motion by the Big Bang, was gradually slowing down due to the collective gravity of all matter. The only question was whether it would slow to a gentle halt or eventually reverse into a cataclysmic crunch. Two independent teams set out to measure this cosmic deceleration by studying a special kind of stellar explosion, a Type 1, a supernova. These explosions are cosmic standard candles, meaning they always erupt with the same intrinsic brightness. By observing how bright they appear from Earth, astronomers can calculate their precise distance. By also measuring how much their light is stretched or redshifted by the expanding universe, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The results were not just surprising, they were paradigm-shattering. The distant, ancient supernova were dimmer than expected. This meant they were farther away than the slowing expansion model predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was counteracting gravity and pushing galaxies apart at an ever-increasing rate. This force was named dark energy. The leading explanation, resurrected from an old idea of Albert Einstein's, is the cosmological constant. This proposes that dark energy is not a substance, but a fundamental property of the vacuum of space itself. Empty space, according to quantum physics, is not truly empty. It is a seething foam of virtual particles that constantly flicker in and out of existence. This quantum activity should imbue every cubic centimeter of nothingness with a tiny amount of energy, a vacuum energy that exerts a negative pressure, causing space itself to stretch. This idea, however, leads to perhaps the most embarrassing discrepancy in all of science, known as the vacuum catastrophe. When physicists calculate the theoretical strength of this vacuum energy based on quantum field theory, the number they get is absurdly, monumentally wrong. It predicts a repulsive force one followed by 120 zeros times stronger than what we actually observe. That is not a small rounding error. It is the largest mismatch between theory and observation in the history of human knowledge. If the theoretical value were correct, the repulsive force would have been so immense that the universe would have blown itself apart instantly after the Big Bang, preventing stars, galaxies, or life from ever forming. The fact that we are here to measure it means our understanding of the vacuum, of quantum physics, or of gravity itself is profoundly incomplete. The ultimate implication of dark energy is a cold and lonely cosmic fate. If this acceleration continues unchecked, dark energy will become the dominant force in the universe. In the distant future, perhaps hundreds of billions of years from now, the expansion of space will outpace gravity's ability to hold structures together. Galaxy clusters will be the first to drift apart, becoming isolated islands in a vast, darkening sea. Then, individual galaxies will be torn apart, their stars scattered into the void. Eventually, even the bonds holding solar systems and planets together may be overcome. The cosmos will end not in fire or ice, but in a profound and irreversible silence, as every particle is pushed beyond the horizon of every other, leaving a universe of isolated, dark, and dying embers. Dark energy is the quiet, relentless architect of that final solitude. The chilling solitude promised by dark energy is punctuated by sudden, violent screams. Across the cosmos, in galaxies billions of light years away, something unleashes more energy in a single millisecond than our sun emits in 3 days. These are fast radio bursts, and for over a decade, they were the universe's most fleeting and frustrating ghost. The first was discovered in 2007, buried in archival data from the Parkes Radio Telescope in Australia. It was a spike of radio waves so intense and so brief that for years many astronomers dismissed it as a glitch, perhaps from a malfunctioning microwave oven at the observatory. But then more were found. Each was a singular event, a brilliant flash from a random point in the sky that never repeated. Were these the final death cries of cataclysmic events, a star being shredded by a black hole or 2 neutron stars colliding? The random, one-off nature pointed to something destructive, a cosmic button pressed only once. Then, in 2016, everything changed. Astronomers found an FRB that did repeat. Not on a schedule, but in unpredictable clusters. This was the key that unlocked the mystery, proving the source was not destroyed in the blast. It could scream into the void over and over again. The hunt to identify the culprit narrowed to some of the most extreme objects in the universe. The prime suspect today is the magnetar, a type of neutron star with a magnetic field so powerful it could erase a credit card from halfway to the moon. Theorists suggest that starquakes on the surface of these hypermagnetic corpses, or sudden magnetic reconnection events, could launch titanic bursts of energy that we see as an FRB. In 2020, this theory got a monumental boost. For the first time, an extremely bright radio burst was detected coming from a known magnetar within our own Milky Way galaxy. It was not as powerful as the distant extragalactic FRBs, but it was the same type of phenomenon happening right in our cosmic backyard, finally linking a specific object to the signal. Yet, even with this breakthrough, puzzles remain. Some FRBs are too powerful, too energetic, to be easily explained by even the most violent magnetar starquake. This leaves the door open, just a crack for wilder possibilities. Could they be produced by cosmic strings, hypothetical defects in the fabric of space-time left over from the Big Bang? Or, in the most speculative corners of thought, could they be evidence of something else entirely, like beams from immense light sails powering interstellar spacecraft of an advanced civilization? While that idea is a last resort for scientists, its very consideration highlights how bizarre these signals truly are. Today, a new generation of telescopes, like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, scans the entire northern sky every day, catching dozens of these bursts each week. Each detection, especially of a new repeater, is a clue. By tracing the burst's path through the diffuse gas between galaxies, astronomers can use it as a cosmic probe to weigh the unseen matter in the universe. These millisecond flashes are more than just mysteries. They are becoming tools, illuminating the dark corners of the cosmos, one brilliant, enigmatic pulse at a time. What other secrets might be hidden in their fleeting light? While magnetas scream across cosmic distances, a much quieter mystery was unfolding much closer to home, not in the void of space, but in the silent drift of two human-made travelers. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were pioneers in every sense. They were the first to venture through the asteroid belt, the first to send back stunning close-ups of Jupiter and Saturn, and the first human objects on a trajectory to leave our solar system entirely. For decades after their primary missions ended, NASA's Deep Space Network continued to listen to their faint radio signals, using the precise Doppler shift of those signals to track their position and velocity across billions of miles. By the late 1980s, a team of scientists led by John Anderson noticed something peculiar in the data. Both spacecraft, now speeding toward the outer darkness, were not quite where our best models predicted they should be. An incredibly subtle but persistent force was acting upon them, a tiny, unexplained acceleration pulling them back toward the sun. It was minuscule, about 10 billion times weaker than the gravity we feel on Earth's surface. To put that in perspective, it was equivalent to the gravitational pull of a single grain of sand held in your hand. But in the hyper-precise realm of celestial navigation, where calculations account for the gravitational tugs of every planet and the gentle push of sunlight itself, this anomaly was a glaring, persistent error. It became known as the Pioneer anomaly. For over 2 decades, it was a thorn in the side of physicists. Could this be a sign of new physics? Did our understanding of gravity break down at the vast distances of the outer solar system? Exotic theories flourished. Some proposed modifications to Einstein's theory of general relativity. Others wondered if it was evidence of unseen, diffuse dark matter dragging on the spacecraft. The possibility, however faint, that we had stumbled upon a fundamental flaw in our cosmic rulebook was electrifying. The true answer, as is often the case in science, lay in a meticulous, grueling process of elimination. The investigation became a masterclass in forensic astronomy. Teams of researchers spent years reconstructing every conceivable force acting on the distant probes. They modeled the gentle pressure of the solar wind. They calculated the tiny thrust from even microscopic gas leaks from the spacecraft's attitude control systems. They accounted for the recoil from the radio signals themselves being beamed back to Earth. One by one, these effects were quantified and dismissed. They were too small to explain the anomaly. The breakthrough came from considering not an external force, but an internal one: heat. The Pioneer probes were powered by radioisotope thermoelectric generators, essentially nuclear batteries that use the decay of plutonium to generate electricity. This process also produced a significant amount of waste heat. The spacecraft were designed with heat radiating outward from their central bus. Crucially, this radiation was not perfectly symmetrical. More heat was emitted from the back of the spacecraft, which faced away from the sun and deep space, than from the front, which was partially shielded by the large dish antenna always pointed at Earth. This anisotropic or directionally uneven thermal radiation acted like a tiny photon rocket. Each infrared photon carrying heat away from the spacecraft also carried a minuscule amount of momentum. Because more photons were pushing off the back than the front, the net effect was a very slight, continuous push back toward the Sun. When scientists finally completed a comprehensive, detailed thermal model of the entire spacecraft, factoring in the heat from the power sources, the electronics, and even the warmth reflected off the antenna dish, the numbers aligned. The thermal radiation pressure matched the anomalous acceleration almost perfectly. The consensus today is that the Pioneer anomaly has been solved, a testament to human ingenuity and relentless attention to detail. Yet a whisper of uncertainty remains for some. The thermal model is extraordinarily complex, and while it explains the vast majority of the drift, a tiny, residual sliver of the effect might still be unaccounted for. This lingering doubt is not a call for new physics, but a powerful lesson. It teaches us that in the quest to understand the universe, our greatest challenges often come not from the stars, but from understanding our own creations down to the most exquisite detail. The anomaly serves as a permanent reminder that before we invoke the shadows of new cosmic laws, we must first shine a light on every last watt of heat escaping into the dark. The meticulous accounting that solved the Pioneer mystery, however, only deepened another. When spacecraft swing by Earth to steal a little of our planet's orbital energy, a cosmic slingshot maneuver perfected over decades, they are supposed to follow a script written by Newton and Einstein. Their speed and trajectory can be predicted with breathtaking precision. Yet, on several occasions, our robotic explorers have delivered a performance with an unscripted and utterly baffling ad-lib. This is the flyby anomaly. It was first clearly noticed with the Galileo spacecraft in 1990, as it whipped past Earth to gain momentum for its long journey to Jupiter. Tracking stations measured its velocity using the Doppler shift of its radio signal. After the flyby, Galileo was moving just a tiny bit faster than all our complex gravitational models said it should be. The difference was minuscule, a change in speed of about 4 millimeters per second. But in the world of orbital mechanics, where calculations are exacting enough to thread a needle at 1 billion miles, that blip was a glaring error. The anomaly did not go away. It appeared again with the Near-Shoemaker spacecraft in '98, and later with the Rosetta and Messenger missions. Sometimes the spacecraft gained a tiny, unexplained boost like Galileo did. Other times, like with the flyby of the Cassini probe, it seemed to lose a minuscule amount of speed. The pattern was inconsistent, but the fact of the anomaly was undeniable. Something was giving these passing spacecraft an unplanned and unmodeled nudge. Engineers and physicists scrambled for an explanation. Was it something exotic, like an interaction with the Earth's rotational frame dragging effect, a subtle warping of space-time caused by our spinning planet that general relativity predicts? The numbers did not quite match. Could it be unmodeled atmospheric drag at extremely high altitudes, where tenuous gases might impart a tiny bit of friction? That, too, failed to fully account for the observations. Perhaps it was an issue with how we model the Earth's gravity field itself, or even the subtle pressure from radio waves bouncing between the spacecraft and our ground antennas. Each idea was explored, and each fell short of providing a universal solution that explained every single anomalous flyby. The flyby anomaly stands as a quiet, persistent hum in the data, a reminder that even our most trusted celestial choreography might have a step we have not yet learned. It is a puzzle not of the distant cosmos, but of our own celestial doorstep, proving that some of the universe's most confounding secrets can be found in the subtle drift of a spacecraft saying one last goodbye to home. While the flyby anomaly is a whisper in our own backyard, the next mystery shouts from over 1,000 light-years away. In the constellation Cygnus, a star named Cassi 8462852, but better known as Tabby's star, does something no other star we have ever seen does. It flickers and fades in bizarre, unpredictable ways, as if something vast and impossible is passing in front of it. The story begins not with a professional astronomer, but with a global team of citizen scientists. They were part of the Planet Hunters project, sifting through the torrent of data from NASA's Kepler Space Telescope, which stared at one patch of sky for years, looking for the telltale, periodic dimming caused by planets crossing their stars. Most dips were gentle, orderly, and small, less than 1%. Tabby's star was different. In 2011, volunteers flagged it as bizarre and interesting. When astronomer Tabitha Boyajian, whom the star is nicknamed for, led the detailed analysis, she found a light curve that defied all logic. There were deep, irregular dips in brightness. One event saw the star's light drop by a staggering 22% for days. That is not a planet. Even a Jupiter-sized world would block only about 1% of a star like this. To cause such an extreme dimming, the object had to be colossal, covering nearly a quarter of the star's fiery face. And then the dips did not repeat on a schedule. They were erratic, chaotic, and asymmetrical, sometimes with sharp drops and slow recoveries. The hunt for an explanation launched 1,000 theories, ranging from the plausible to the spectacular. The first natural idea was a gigantic swarm of comets, perhaps hundreds of thousands of them, torn apart by the star's gravity and creating a thick, irregular cloud of dust and debris. But to block that much light, the swarm would have to be on an unimaginable scale, a scenario many found difficult to swallow. Then came the idea that captured the world's imagination, a Dyson sphere. This is a hypothetical megastructure, a concept from science fiction where an advanced civilization completely surrounds its star with solar collectors to harness all its energy. What if we were seeing a partially built or a broken Dyson swarm? The irregular dips could be vast arrays of orbiting panels or collectors passing in front of the star. For a moment, it was the most tantalizing potential evidence of intelligence beyond Earth we had ever encountered. The star became a focal point for SETI, the search for extraterrestrial intelligence, with radio telescopes listening for any engineered signals. They heard nothing but cosmic silence as more data poured in, particularly from the Los Cumbres Observatory Global Telescope Network. A clearer, dustier picture emerged. Detailed analysis of the star's light during dimming events revealed a crucial clue. The star dimmed more in blue light than in red light. That is the signature of dust. Small particles scatter blue light more effectively, letting redder light pass through. A solid object like a planet or a massive alien megastructure would block all colors of light equally. This pointed strongly to a natural, if extraordinary, explanation. The leading theory now suggests the star is surrounded by a complex, dynamic cloud of fine, circumstellar dust, possibly from the breakup of a moon or a planet, creating an ever-shifting veil that causes the wild dimming. Yet, even this explanation has its own mysteries. Where did all this dust come from, and why is it behaving so erratically? Tabby's star did more than just puzzle astronomers. It sparked an entirely new field of study. It taught us to look for other stars with unusual dimming patterns, a category now called Boyajian star analogues. It proved the incredible value of citizen science in discovering cosmic anomalies that algorithms might overlook. And it remains under constant watch, a flickering beacon reminding us that the universe is always more inventive than our wildest fiction, capable of crafting mysteries that sit perfectly on the razor's edge between a natural cataclysm and a signature of intelligence. The erratic dance of dust around a distant star is a puzzle of shadow and light, but our next phenomenon is a masterpiece of geometric perfection, painted in the swirling clouds of a world in our own solar system. At Saturn's North Pole, a storm rages that is unlike anything else we have ever seen. It is not a chaotic spiral or a simple circular vortex, but a perfect, colossal hexagon. This six-sided cloud pattern, first glimpsed by the Voyager probes in the 1980s, was so bizarre that many scientists doubted the initial images. It seemed like a trick of the camera, an artifact of data processing. But when the Cassini spacecraft arrived at Saturn decades later, it was still there, a persistent and breathtaking feature etched into the planet's atmosphere. The scale is almost incomprehensible. Each side of the hexagon is longer than the diameter of Earth. The entire structure is so vast that 2 or even 3 of our entire planets could fit comfortably inside its boundaries. And it is not static, it is a raging jet stream, a river of wind screaming along the hexagonal path at speeds of over 200 miles per hour, with a colossal rotating storm sitting directly at its center. For over 40 Earth years, through multiple Saturnian seasons, this precise shape has held its form. How does nature create and maintain such a sharp, geometric feature in the turbulent, gaseous atmosphere of a giant planet? On Earth, we see circular hurricanes and meandering jet streams, but never a polygon with straight sides and sharp 120-degree corners. The leading clue comes not from astronomy, but from the physics of your kitchen sink. In laboratory experiments, when a fluid is rotated in a circular container, and a smaller, central disk rotates at a different speed, standing waves can form in the fluid between them. At certain speeds, these waves naturally organize into polygons, squares, triangles, and yes, hexagons. This suggests Saturn's hexagon is likely a giant standing wave pattern in the planet's fast-moving north polar jet stream, shaped by the complex interaction between different layers of the atmosphere rotating at different speeds. The hexagon is essentially a self-organizing, stable pattern in a swirling fluid, a natural resonance. Yet calling it a standing wave only deepens the mystery. The exact recipe of wind speeds, atmospheric densities, and planetary rotation that locks this pattern in place for decades is fiendishly difficult to replicate in computer models. Why a hexagon and not an octagon or a square? Why is it so preternaturally stable when the rest of the planet's weather is dynamic and changing? The fact that we see nothing like it at Saturn's south pole, which has a more conventional circular hurricane, adds another layer of intrigue. Cassini's detailed observations revealed that the hexagon is a towering structure, reaching hundreds of miles vertically into the stratosphere, with its shape influencing weather layers far above the cloud tops we can see. This longevity and vertical reach imply a profound connection between the deep interior dynamics of Saturn and its upper atmosphere, a connection we are only beginning to decipher. The Great Hexagon is a cosmic demonstration that the laws of physics can paint with a ruler and protractor, crafting a storm of such precise and enduring beauty that it challenges our very understanding of fluid chaos. It is a permanent monument to the hidden order within the whirlwind. The geometric perfection of Saturn's storm exists within a single, stable system, but our entire galaxy is caught in a relentless, unseen current. Far beyond the familiar stars of our own Milky Way, something immense is pulling us and everything in our local galactic neighborhood toward a specific point in the cosmic dark. This is the Great Attractor, and its discovery rewrote the map of our place in the universe. For decades, astronomers understood that most galaxies are moving away from us due to the expansion of space, a motion measured by their redshift. But in the 1970s and 80s, detailed surveys began to reveal something more peculiar. Galaxies, including our own, also have individual sideways motions called peculiar velocities, deviations from the smooth Hubble flow of expansion. When scientists mapped these drift patterns, a shocking truth emerged. Our Milky Way, along with our entire local group of galaxies and the immense Virgo supercluster it belongs to, is all streaming at over 1 million miles per hour toward a specific region of space near the constellation Norma. The source of this colossal pull was named the Great Attractor. The mystery was compounded by a frustrating cosmic blind spot. The direction of this pull lies directly behind the crowded, dusty plain of our own galaxy, an area astronomers call the zone of avoidance. Imagine trying to see a distant mountain range through a dense, glowing fog. That is what our view toward the Great Attractor is like. The thick band of stars, gas, and dust in the Milky Way's disk obscures almost all visible light from that region, hiding the true nature of the gravitational culprit for years. It was like feeling a powerful tide but being unable to see the moon causing it. The breakthrough came with instruments that could see through the veil. Using radio, infrared, and X-ray telescopes which can penetrate interstellar dust, astronomers began to map the hidden landscape. They discovered the Great Attractor is not a single, unimaginably dense object, but a massive concentration of mass, an enormous supercluster of galaxies. The Norma cluster sits at its heart, a dense knot of galaxies, and it is surrounded by other massive clusters, all bound together by gravity in a structure now called the Laniakea supercluster, of which our Milky Way is a distant outlying suburb. Yet, even with this mapping, the puzzle is not fully solved. The sheer amount of visible mass in the Norma cluster and its surroundings, while enormous, does not seem sufficient to account for the full strength of the gravitational pull we are experiencing. This suggests there is even more hidden mass there, vast reservoirs of dark matter weaving through the supercluster, amplifying its gravitational reach. Furthermore, our entire Laniakea supercluster itself appears to be in motion, pulled by something even greater and more distant, a structure known as the Shapley Attractor. This reveals a cosmic truth. The universe is structured like a vast hierarchical web, with galaxies flowing along great rivers of gravity toward dense nodes of mass. The Great Attractor is not our final destination, but a major waypoint in an epic billion-year journey we are all undertaking, a silent testament to the fact that even in the grand theater of the cosmos, we are not the audience, but actors on a stage whose full dimensions we are only beginning to perceive. That immense cosmic current pulling our galaxy is charted by the drift of billions of stars, but in 2017, an object from that distant river arrived in our own celestial harbor. It was a visitor from interstellar space, the first we had ever seen, and it defied every expectation. The Pan-STARRS telescope in Hawaii spotted it first, a faint point of light already speeding away from the sun after its closest approach. They named it Oumuamua, a Hawaiian term meaning scout or messenger from the distant past. From the moment of its discovery, it was clear this was no ordinary asteroid from our own solar system. Its hyperbolic orbit, a steep, open curve, proved it was not bound to our sun. It was just passing through, a cosmic tourist on a billion-year journey between stars. But as astronomers trained their most powerful instruments on it, the strangeness deepened. The first shock was its shape. By measuring how its brightness changed dramatically as it tumbled, scientists deduced Oumuamua was highly elongated, perhaps 10 times as long as it was wide. Think of a cigar or a pancake tumbling chaotically through the void. Nothing in our solar system, at least nothing of its estimated size, looks quite like that. The second shock was what it lacked. As it sped away from the sun, telescopes watched closely for any sign of outgassing, the release of gas and dust that forms the characteristic fuzzy coma and tail of a comet. They saw nothing, no gas, no dust, no coma. This ruled out a typical comet, yet its behavior suggested otherwise. This was the third and most profound anomaly. Precise tracking of Oumuamua's path revealed it was not just coasting under the sun's gravity alone. It was accelerating ever so slightly on its way out of the solar system. Something was giving it an extra push. For a comet, this is easily explained by outgassing, the jetting of material acting like a natural rocket engine. But Oumuamua showed no visible outgassing, no dusty trail. So what was pushing it? The scientific community scrambled for natural explanations. One leading idea proposed it was a comet after all, but an exotic one made of different stuff. Perhaps it was composed largely of solid nitrogen ice, like a chunk from a distant Pluto-like world. As the sun warmed it, the nitrogen could have sublimated directly from solid to gas, providing the thrust without releasing the dusty debris a water ice comet would. Another theory suggested it was a hydrogen iceberg, outgassing pure hydrogen that our telescopes could not see. Yet each of these ideas required Oumuamua to be made of materials in a way that stretches our understanding of how objects form in interstellar space. Into this debate stepped Harvard astronomer Avi Loeb with a provocative and far more sensational hypothesis. Could Oumuamua's acceleration be explained by radiation pressure from the Sun? If the object were extremely thin and lightweight, sunlight itself could push on it like a sail. This led to the suggestion that Oumuamua might be artificial debris, a discarded light sail from an advanced technological civilization drifting between the stars. The elongated shape in this scenario could be that of a broken sail. The scientific consensus firmly favors a natural origin, noting that extraordinary claims require extraordinary evidence, and a novel natural explanation is more likely than an interstellar artifact. The hydrogen iceberg theory, while speculative, fits the observed acceleration without visible debris, but the core of the mystery remains untouched. We simply did not get a good enough look. By the time we knew it was there, Oumuamua was already receding, too faint and too small for our telescopes to resolve its shape or surface. We observed it for only a few frantic weeks before it vanished into the darkness from whence it came. It is now gone, forever beyond our reach, its secrets locked within its silent, tumbling form. Oumuamua's legacy is not an answer but a profound question. It proved interstellar visitors are real and that they can be utterly unlike anything in our own celestial backyard. It was a single, enigmatic data point, a messenger that delivered its cryptic note and departed before we could fully learn its language. Oumuamua's fleeting passage was a singular event, but the next mystery is written across the entire sky, a faint whisper from the beginning of everything that seems to be telling us we are special in a universe that should not allow it. This is the axis of evil, a name cosmologists gave with a mix of drama and dread to a pattern they desperately wish was not there. It is found in the oldest light we can see, the cosmic microwave background radiation. This is the afterglow of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old, now cooled to a faint microwave glow that permeates all of space. According to our fundamental cosmological principle, the universe on the largest scale should be isotropic and homogeneous. In plain terms, it should look the same in every direction, with no preferred axis, no center, and no edges. The CMB, in most ways, confirms this beautifully. It is almost perfectly smooth, with tiny temperature variations of just 1 part in 100,000, the seeds from which all galaxies would eventually grow. But when scientists created exquisitely detailed maps of these fluctuations, like the ones from the Planck satellite, they noticed something unsettling. The patterns of hotter and colder spots are not completely random. They appear to have a subtle alignment or correlation with the plane of our own solar system and our galaxy's motion through space. It is as if the blueprint of the entire cosmos has a faint watermark that points directly back to us. This is profoundly troubling. Our location in the universe is supposed to be utterly ordinary, a cosmic principle called the Copernican principle. The CMB is light from a time long before our solar system or galaxy existed. There is no possible causal connection between the structure of the infant universe and the orientation of our little planetary system billions of years later. Finding one would be like discovering that the cracks in ancient pottery always align with the floorboards in your modern kitchen. It suggests a contamination, a flaw in our perception, or something far more revolutionary. Scientists have explored every possible mundane explanation. Could it be an artifact of how we process the data, or contamination from dust within our own Milky Way galaxy obscuring the true signal? Teams have scrutinized the data for over a decade, and while foreground effects can account for some of the signal, a stubborn, low-level alignment seems to persist. If it is not a fluke and not contamination, the implications are staggering. It could mean our standard model of cosmology is incomplete. Perhaps the universe is not isotropic on the very largest scales, but has a preferred direction, a cosmic texture imprinted from an era before the Big Bang we know. Some speculative theories even suggest it could be evidence of our universe colliding with another bubble universe in a vast multiverse, leaving a bruise on the sky. Most cosmologists, cautious by nature, still lean toward the anomaly being a complex statistical fluke, a trick of the eye when looking at a limited data set. Yet, its provocative name endures because it represents the ultimate scientific anxiety, a hint that our place in the cosmos might not be so humble after all, and that the universe's first light carries a message we have not yet learned how to read. That faint watermark on the cosmic background speaks to a universe of hidden structure, but our inventory of its most basic building blocks is still shockingly incomplete. We are missing half of the ordinary matter in the cosmos. This is not the mysterious dark matter or dark energy, but the stuff we are made of, the protons and neutrons known as baryonic matter. Everything you can see and touch, every star, every planet, every person, is made from this baryonic material. According to the precise measurements of the Big Bang's aftermath, a process called Big Bang nucleosynthesis, we can calculate exactly how much of this ordinary matter the universe should have created. It is a cosmic budget, and the numbers are very precise. Yet, when astronomers take a census of all the baryons they can see in the relatively recent universe, adding up all the stars, all the glowing gas in galaxies, all the dust, they come up staggeringly short. Only about 50% of the expected baryons are accounted for. Billions upon billions of suns worth of ordinary atoms have simply vanished from our ledgers. So where did half the universe go? The leading suspect is not a place, but a state of being. Theorists believe the missing baryons are not in dense, shining objects, but spread out in an immense, diffuse web of superheated gas that stretches between galaxies. This is the warm, hot intergalactic medium, or the WIM. Picture it not as a fog, but as the faint, steamy breath exhaled by the cosmic web itself. After the Big Bang, gravity pulled matter into vast filaments and sheets, the scaffolding for all cosmic structure. As gas flowed along these filaments into dense knots that became galaxy clusters, it did not move smoothly. It crashed, shocked, and heated to temperatures between 100,000 and 10 million degrees. This transformed the gas into a thin, ionized plasma, so hot it glows not in visible light, but primarily in far ultraviolet and soft X-rays. Detecting it is like trying to see the heat shimmer above a desert highway from an airplane. For decades, it remained entirely theoretical, the perfect hiding place for our missing atoms. The hunt to find the WIM has been a painstaking effort in cosmic forensics. Astronomers use distant, brilliant objects as backlights. When the light from a faraway quasar travels billions of light years to reach us, it passes through these intergalactic filaments. Atoms in the WIM, even at such low density, will absorb very specific wavelengths of that light. By looking for the faint fingerprints of highly ionized oxygen and other elements in the quasar spectrum, scientists can confirm the presence and measure the properties of this elusive gas. Recent observations from powerful X-ray telescopes like XMM Newton and Chandra have begun to turn theory into reality. They have detected the telltale absorption lines from the WIM in the spectra of distant quasars, and even seen the faint X-ray glow from the densest parts of these filaments as they wrap around massive galaxy clusters. Each detection is a hard-won clue, a few more atoms checked off the missing list. The story these observations tell is of a universe where the ordinary matter is not merely in the islands of galaxies, but in the vast, hot ocean that connects them. Finding the WIM is more than solving an accounting error. It is mapping the bloodstream of the cosmos, the hidden channels through which the raw material for future stars and worlds silently flows. Mapping the universe's missing atoms is a delicate accounting of the present, but our most precise ledger comes from its very first minutes. There, in the searing heat just after the Big Bang, a different and more fundamental accounting error persists. This is the lithium problem, and it represents a quiet but profound crisis in our understanding of cosmic origins. In those initial moments, the universe was a primordial fusion reactor. For a brief window, temperatures and densities were perfect for protons and neutrons to collide and fuse into the lightest elements: hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, is not just a theory, it is a cornerstone of modern cosmology. The calculations that predict how much of each element was forged are exquisitely precise, relying on well-measured nuclear physics and the known density of ordinary matter. For hydrogen and helium, the predictions match the observed abundances in the oldest stars and primordial gas clouds almost perfectly. It is a stunning success. But for one specific isotope, lithium-7, the numbers spectacularly disagree. The models tell us the infant universe should have created about 1 lithium-7 atom for every 10 billion hydrogen atoms. Yet when astronomers point their telescopes at the oldest stars in our galaxy, relics from near the dawn of time, they measure only about 1/3 of that amount. The universe seems to have come up short on lithium from day one. This is not a small discrepancy. It is a factor of 3, a glaring mismatch between our most fundamental theory of the cosmos's first moments and the fossil evidence we can actually observe. Solving it has become a cosmological obsession. One line of investigation looks inward at the stars themselves. Could these ancient stars have somehow destroyed their original lithium over billions of years? As a star ages, surface lithium can be dragged down into hotter interior layers by convection and burned up in nuclear reactions. Some models suggest this process could be more efficient than we thought, especially for certain types of old metal-poor stars. But this explanation is messy. It requires a specific and universal stellar behavior that seems difficult to reconcile with the variety of stars we observe. The other, more radical line of investigation looks back to the Big Bang itself. Could our understanding of nuclear physics in that extreme environment be incomplete? Perhaps unknown particles, like certain types of dark matter, were present and altered the nuclear reaction rates in those first few minutes, suppressing lithium production. Or maybe our measurements of the key nuclear cross-sections in laboratories on Earth have subtle, unaccounted for errors that throw off the entire calculation. Each proposed fix, however, tends to create new problems. Tweaking the physics to reduce lithium-7 often inadvertently ruins the perfect agreement we have for hydrogen and helium. It is a cosmic balancing act where adjusting one number throws the entire delicate equation into disarray. The lithium problem endures because it is so clean and so specific. It is not a vague anomaly lost in noise. It is a precise numerical prediction that the universe appears to have defied. This tiny mismatch for a single isotope stands as a permanent reminder that our story of creation, for all its brilliance, may still be missing a page, a subtle piece of physics from the universe's first breath that we have yet to comprehend. The quiet accounting error of lithium is a puzzle of the universe's first moments, but the cosmos also fires bullets of pure energy directly at us. These are ultra-high energy cosmic rays, and they are the most energetic particles ever observed in nature. They are not rays of light, but subatomic particles, often single protons, traveling at a hair's breadth from the speed of light. When one of these particles, smaller than an atom, slams into Earth's upper atmosphere, it unleashes a catastrophic cascade of secondary particles, an air shower that can spread over dozens of square kilometers by the time it reaches the ground. The energy packed into that single proton is mind-numbing. The most powerful ones carry kinetic energy equivalent to a well-thrown baseball, concentrated into a subatomic speck. This is over 100 million times more energy than the protons we can accelerate in our most powerful human-built machine, the Large Hadron Collider. Nature is firing a particle accelerator at us that we cannot hope to replicate, and that presents a profound mystery. According to our understanding of physics, these particles should not be able to reach us at all. Space is not empty. It is filled with the faint relic radiation from the Big Bang, the cosmic microwave background. For a proton traveling at near light speed across hundreds of millions of light years, this background radiation is not a gentle glow. It is a thick fog of high-energy photons. When an ultra-high-energy proton collides with one of these microwave photons, it loses a significant amount of energy in a process called the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. It is like a marathon runner trying to sprint through a field of dense, sticky mud. Over intergalactic distances, this effect should completely sap the energy of any proton above a certain threshold before it ever gets close to Earth. Yet we keep detecting them. They are arriving with energies that, by all rights, should have been drained away by the cosmic microwave background long ago. This means one of two astonishing things. Either these particles are not coming from the distant universe as we assume, but from somewhere much, much closer within our own galactic neighborhood, a prospect that creates its own set of theoretical headaches. Or our understanding of particle physics at these extreme energies is fundamentally incomplete. The hunt to find the source of these cosmic bullets is a global endeavor. Because they are so incredibly rare, perhaps just one particle per square kilometer per century at the very highest energies, detection requires a colossal trap. The Pierre Auger Observatory in Argentina is just that. It covers an area of 3,000 square kilometers, about the size of Rhode Island, with over 1,600 water tank detectors spread across the Pampas Plains. They do not catch the primary particle. It never reaches the ground. Instead, they detect the faint flashes of Cherenkov light produced by the shower of secondary particles raining down. By triangulating the timing of these flashes across the vast array, scientists can reconstruct the direction the original cosmic ray came from. The data points to likely sources outside our own Milky Way galaxy, often in the direction of active galactic nuclei, the furious cores of distant galaxies powered by supermassive black holes. Yet, pinning down a specific source remains maddeningly difficult. These particles are not guided by magnetic fields in a straight line. Their paths are bent and scrambled as they traverse the tangled magnetic fields of intergalactic space, making it impossible to trace them back to a single, precise point of origin. Each detection is a message from a cosmic cannon, but the return address has been blurred beyond recognition. They are the universe's most energetic envoys, carrying secrets about the most violent places in existence and challenging the very laws we believe govern their impossible journey. Deep within the heart of our own galaxy, a silent, brilliant fog of light defies easy explanation. This is the galactic center excess, a mysterious glow of high-energy gamma rays emanating from the region around the supermassive black hole at the Milky Way's core. For over a decade, since the Fermi Gamma Ray Space Telescope began its relentless scan of the sky, this excess has captivated and divided astrophysicists. It is not the chaotic light of stars or gas, but a smooth, spherical halo of gamma radiation that extends for thousands of light years. The puzzle is not its existence, but its origin. What is creating this persistent, energetic fog at the very center of our cosmic home? The initial suspicion fell on the usual suspects, pulsars. These are the rapidly spinning, city-sized corpses of dead stars, lighthouses of the cosmos that beam out radiation. In particular, a vast population of ancient, recycled pulsars called millisecond pulsars could be the culprit. They are faint and difficult to spot individually at such a great distance, but collectively, thousands of them could produce a diffuse, spherical glow that matches the Fermi data remarkably well. This explanation is appealing because it uses known astrophysics. We have seen millisecond pulsars elsewhere, and the galactic center is a crowded, ancient place where they should naturally accumulate. Yet there is a compelling and far more exotic alternative. This smooth, spherical excess is exactly what many theoretical physicists predicted we might see if dark matter particles were annihilating with one another. According to this idea, the dense core of our galaxy is also a dense core of dark matter. When two of these hypothetical particles collide, they could annihilate in a flash of energy, producing the gamma rays that Fermi sees. The shape of the signal is key. A dark matter halo would naturally produce a smooth, round glow, while a collection of distinct point sources like pulsars might show more lumpiness or clustering. This is where the scientific debate intensifies. Proponents of the pulsar model point to recent studies that have identified faint point sources within the excess, suggesting it may indeed be made of many unresolved stars. They argue that as telescopes improve, we will simply resolve more and more pulsars, gradually chipping away at the mysterious glow until nothing unexplained remains. On the other side, dark matter advocates note that the energy spectrum of the gamma rays, their specific brightness at different energies, matches certain predictions for dark matter annihilation better than it does for known pulsar populations. It is a classic standoff between a conventional but complex astrophysical explanation and a revolutionary one that hinges on the universe's most elusive substance. The resolution will not come from argument but from sharper eyes on the sky. The next generation of gamma-ray telescopes and radio surveys will provide the crucial evidence. If the excess truly dissolves into a sea of pinpoint pulsar sources, it will be a monumental discovery in stellar archaeology, revealing a hidden population of ancient stars. But if the glow remains stubbornly smooth and unresolved, it could be our first direct glimpse of dark matter's invisible hand, not through its gravity but through its self-destruction. The answer lies in that faint, spherical fog, a cosmic Rorschach test where scientists see either the ghosts of dead stars or the signature of the universe's missing skeleton. The smooth glow at our galaxy's center asks what holds it together, but that question has a much deeper answer written in the motion of every star within it. We have already seen how the strange rotation of galaxies provides the strongest evidence for dark matter, that invisible halo holding the cosmos together. But what if the evidence is pointing somewhere else entirely? What if the problem is not with what is missing from our universe, but with the fundamental laws we use to describe it? This is the radical proposition of modified Newtonian dynamics, or MUND, a theory that dares to rewrite gravity itself to avoid the need for dark matter. The core idea is beautifully simple, and it begins with a single, critical observation. In a galaxy, stars experience an incredibly weak gravitational pull, especially those far out in the sparse outskirts. The accelerations involved are minuscule, far below what we can test in our solar system or laboratories. Mund proposes that Newton's famous law of gravity, and by extension Einstein's general relativity, breaks down at these extremely low accelerations. It suggests a new, modified rule. Below a certain critical threshold of acceleration, gravity stops falling off with the square of the distance and instead falls off more slowly. This tiny tweak to the math has a profound consequence. When you apply Mund's modified formula to a spiral galaxy, you plug in only the visible mass of its stars and gas. Out comes a predicted rotation curve, and for many galaxies, that prediction matches the observed flat curve almost perfectly, without adding a single gram of invisible dark matter. The stars whip around as fast as they do not because of an unseen halo, but because gravity itself is stronger in the realm of the very faint. This is not just a mathematical trick. Mund has scored some surprising predictive successes. It accurately forecasts the relationship between a galaxy's visible mass and its rotation speed, a tight correlation that the standard dark matter model struggles to explain without additional assumptions. For certain types of small, diffuse galaxies where dark matter models often fail, Mund predictions fit the data remarkably well. It treats the visible universe as complete, arguing that what you see is truly what you get, and that the anomaly is in our equations, not in our inventories. Yet, for all its elegance on the galactic scale, man faces a universe-sized problem. When we zoom out to the colossal structures of galaxy clusters, the theory stumbles. The visible mass in these clusters is nowhere near enough to provide the gravity needed to hold them together, even with modified laws. The same is true for the gravitational lensing we see around clusters. The bending of light is far too strong to be explained by the visible matter alone, even with adjusted gravity. To salvage the theory, proponents must still invoke some form of unseen matter, perhaps a new type of neutrino, which begins to look suspiciously like the dark matter it was meant to replace. Furthermore, man struggles to explain the detailed blueprint of the early universe imprinted on the cosmic microwave background. The distribution of matter that created the galaxies we see today required the gravitational scaffolding of dark matter. Modified gravity alone cannot replicate that cosmic blueprint. This leaves us at a profound crossroads in physics. Do we accept the existence of a vast, invisible component to the cosmos that outweighs everything we know, a substance that remains frustratingly out of reach? Or do we take the bold step of revising one of humanity's oldest and most successful physical theories, gravity, to fit the observations? It is a choice between inventing a new kind of matter or rewriting a fundamental force. Both paths are extraordinary, and both remind us that our understanding of the cosmos is still a story being written, with its most pivotal chapter yet to come. Rewriting gravity or inventing invisible matter are attempts to fix a cosmic ledger, but our own planet's history presents a ledger of its own that stubbornly refuses to balance. Billions of years ago, when the first single-celled life was stirring in Earth's ancient seas, our sun was a weaker star. According to our detailed models of stellar evolution, a young sun should have been about 30% dimmer than it is today. That faintness presents a chilling paradox. With so much less solar energy reaching our planet, the early Earth should have been a global snowball, a frozen world with oceans locked under miles of ice. The mathematics are clear and unforgiving, yet the geological record shouts the opposite. We have solid evidence of liquid water on the surface from at least 3.8 billion years ago, in the form of ancient sedimentary rocks and zircon crystals. Even more compelling, we have fossils of microbial life itself dating back nearly as far. The planet was not only unfrozen, it was hospitable enough for life to arise and thrive. This is the faint young sun paradox, a contradiction between the physics of stars and the geology of our own world. How did Earth stay warm under a cool sun? The leading solution points to the planet's own blanket, its atmosphere. Today, greenhouse gases like carbon dioxide and methane trap heat and moderate our climate. On the early Earth, the greenhouse effect would have needed to be far more potent. Scientists propose that the ancient atmosphere was much thicker with these gases, perhaps hundreds of times more carbon dioxide than today, creating a super greenhouse that compensated for the faint sunlight. There is another piece to the puzzle, a reflective one. A frozen planet is bright, covered in ice that reflects sunlight back into space, which makes it even colder in a vicious feedback loop. But a warmer, wetter planet with liquid oceans and darker land masses is darker overall, absorbing more of that precious solar heat. This property, called albedo, is critical. The young Earth likely had less continental land, meaning more dark ocean surface and no bright ice caps, so it naturally soaked up more of the sun's feeble light. Still, modeling this ancient climate is a fiendish challenge. Getting the exact mix of gases, the cloud cover, the planetary rotation, and the ocean currents to produce a stable, warm climate for hundreds of millions of years is a delicate balancing act. Some models suggest methane, a powerful greenhouse gas produced by early microbes, may have played an even bigger role than carbon dioxide. Others wonder if the atmosphere contained traces of hydrogen, which could have provided significant warming. The paradox is not fully solved. It is an ongoing negotiation between astrophysics, geology, and climatology. Its greatest lesson, however, extends far beyond our own past. The faint young sun paradox is a beacon of hope in the search for life elsewhere. It proves that a planet's climate is not a simple function of its star's brightness. A world can employ clever atmospheric tricks to keep itself warm and wet even under a faint sun. This expands the traditional habitable zone, the orbital region where liquid water can exist. A planet orbiting a dim star or one farther out from its sun than Earth might still be a living world if it has the right atmospheric composition. Our own Earth's history is the ultimate proof of concept, showing that planetary climates can achieve remarkable stability against cosmic odds, turning a potential deep freeze into a cradle for life. While Earth's early climate was a delicate balancing act, the death throes of a star can forge structures of impossible geometry. In the constellation Monoceros, about 2,300 light-years away, the Hubble Space Telescope captured an image that defies the very idea of cosmic chaos. It is called the Red Rectangle Nebula, and it is exactly that, a stunning, blood-red rectangle of glowing gas hanging in the void. At its heart is a dying binary star system, HD 44179, which has entered its protoplanetary nebula phase. This is a brief, violent window in a star's life, lasting only a few thousand years, where it has cast off its outer layers but is not yet hot enough to make the surrounding gas glow on its own. Instead, the eerie red light comes from a process called luminescence, where dust particles convert the star's harsh ultraviolet radiation into this deep crimson glow. What makes this object a profound mystery is not its existence but its perfection. Most planetary nebulae are beautiful, but they are messy, forming intricate but chaotic bubbles, rings, and butterfly-like shapes. The red rectangle is different. It presents razor-sharp corners and astonishingly straight sides, looking less like an astronomical object and more like a piece of abstract art or a view down a neon-lit tunnel. Hubble's sharp eye revealed an even deeper secret within this geometric shell. The rectangle is not hollow. Spanning its interior like the rungs of a cosmic ladder are a series of evenly spaced horizontal dust lanes. This intricate internal skeleton suggests a process of extraordinary regularity, a clockwork mechanism in the star's death. So how does a dying star create something so precise? Astronomers believe the key lies in the central binary system. As one star shed its outer layers, the gravitational dance of the two stars could have confined the expelled gas into a dense, rotating disk around them, a waste belt of dust. Then powerful jets of material squirted out from the poles of the dying star might have punched through this disk. If the axis of these jets is slowly wobbling or precessing, like a spinning top winding down, they could paint a conical shape in the surrounding gas. From our vantage point, looking almost directly down the barrel of this cone, the edges would appear as straight lines, forming the iconic X shape that frames the rectangle. The regular ladder rungs could then be explained by pulsations from the star itself, ejecting material in rhythmic bursts over hundreds of years, each new shell of dust marking a rung on the ladder. Yet, while this model is elegant, it remains a theory. The exact physics that coordinates this stellar ballet to produce such crisp, long-lived geometry is not fully understood. It requires a perfect alignment of timing, density, and viewing angle that seems almost too fortunate. The red rectangle stands as a breathtaking counterpoint to cosmic randomness. It is a reminder that within the violent, chaotic processes of stellar death, nature can still draft with a ruler and a compass, crafting a monument of temporary, geometric beauty that will, in a cosmic blink, fade back into the formless dark. The geometric perfection of a dying star's nebula is a temporary wonder, but the death of information itself within a black hole threatens to unravel physics forever. This is the black hole information paradox, and it represents a fundamental war between our two greatest theories of reality. On one side stands quantum mechanics, the rulebook for the very small. One of its most sacred principles is the conservation of information. In the quantum world, information is never truly destroyed. If you could somehow track every single particle and every quantum state, you could theoretically reverse time and reconstruct any past event. It is like saying that if you burn a book, the information in its pages is not gone. It is just transformed into the precise arrangement of ash, smoke, and heat. In principle, an all-knowing being could read the smoke and rebuild the book. On the other side stands Einstein's general relativity, our theory of gravity and the very large. It describes black holes in starkly simple terms. Their boundary is the event horizon, a point of no return. Cross it, and you are gone forever from our universe, crushed into the infinitely dense singularity at the center. According to this classical view, everything about you, your mass, your charge, your memories, the very information that made you, is irretrievably lost. For decades, physicists accepted this grim erasure as the price of such extreme gravity. Then, in the 1970s, Stephen Hawking made a shocking calculation. He applied quantum theory near the event horizon and discovered that black holes are not completely black. They should slowly leak a faint glow of particles, now called Hawking radiation. This radiation, he argued, is entirely random and thermal. It carries no information about what fell in. So, over unimaginable eons, a black hole will evaporate, fading away into this random thermal glow. And when it vanishes, all the information about everything it ever consumed vanishes with it, permanently erased from the cosmos. This was the paradox laid bare. Quantum mechanics says information must be preserved. Hawking's calculation said black holes destroy it. One of these cornerstone theories had to be wrong. Hawking was so confident in his finding that he famously made a bet with fellow physicists John Preskill and Kip Thorne, wagering that information was indeed lost forever. For years, this paradox simmered, a deep crack in the foundation of physics. The modern quest to solve it has led to some of the most mind-bending ideas in science. One revolutionary concept is the holographic principle. It suggests that all the information contained within a three-dimensional volume of space, like the interior of a black hole, can be completely encoded on its two-dimensional boundary, the event horizon. Imagine the information of your entire life, every experience and thought, being perfectly stored as a hologram on your skin. When something falls into a black hole, its information is not destroyed but smeared and scrambled across this horizon, eventually leaking out in a highly encrypted form within the Hawking radiation. To an outside observer, you would appear frozen at the horizon, your information slowly radiating away, while from your own perspective you would fall straight through. This leads to another wild proposal, the firewall paradox. If information is preserved on the horizon, then the empty space just outside the black hole, which relativity says should be uneventful, might actually be a searing wall of high-energy particles, a firewall that instantly incinerates anything trying to cross. This idea is deeply troubling as it replaces one paradox with another, violating Einstein's principle that free fall should feel like floating in empty space. In 2004, Stephen Hawking conceded his bet. He presented a new calculation suggesting that black holes could, after all, preserve information in their radiation, though the exact mechanism remains hotly debated. Today, most physicists believe information is somehow preserved, but how is the great mystery? Does it linger in a remnant? Is it hidden in correlations we do not yet understand? The paradox forces us to confront the fact that our theories of the very large and the very small are incompatible at the edge of a black hole. Solving it may require a new theory of quantum gravity, a framework that can describe both the fabric of space-time and the particles within it as a single, coherent reality. This is not just an academic puzzle. It asks what reality truly is, whether the past is set in stone or can be erased, and if the universe itself keeps a perfect, unalterable record of everything that has ever happened. If information itself can be erased by a black hole, the universe has other objects that shred the very rules of matter and magnetism. These are magnetars, the universe's ultimate cosmic magnets. They are a rare and terrifying breed of neutron star, the collapsed core of a giant star that died in a supernova. What sets them apart is a magnetic field of almost incomprehensible power. While a typical neutron star already has a magnetic field 1,000,000,000 times stronger than Earth's, a magnetar's field is another 1,000 times stronger than that. We are talking about a 1,000,000,000 times the strength of the magnet on your refrigerator. At such intensities, physics as we know it breaks down. The field is so strong it can distort the shape of atoms themselves, stretching them into long, thin cylinders. It could wipe the data from every credit card on Earth from halfway to the moon, and these fields are not dormant, they are engines of cosmic violence. Magnetars suffer from starquakes, catastrophic ruptures in their rigid, crystalline crusts. When the crust cracks under the immense strain of the magnetic field, it releases a cataclysm of energy. In a fraction of a second, a magnetar can unleash a flare of gamma rays and X-rays that outshines our entire galaxy. We have felt their power from across the Milky Way. In 2004, a magnetar 50,000 light-years away in the constellation Sagittarius unleashed a blast that, for a fifth of a second, was brighter than a full moon. It actually compressed Earth's upper atmosphere, briefly disrupting long-range radio communications worldwide. This was a direct hit from an object halfway across our galaxy, a testament to the sheer ferocity packed into these city-sized spheres. The central mystery is how such a monstrous magnetic field is born. The leading theory points to a dynamo effect during the star's chaotic birth. When a massive star collapses into a neutron star, it spins faster, just like a figure skater pulling in their arms. If the newborn neutron star is spinning hundreds of times per second, its interior, a superfluid soup of neutrons and protons, can churn violently. This churning, combined with intense heat and insane density, could amplify a pre-existing magnetic field to magnetar levels in a matter of seconds. But the details are hotly debated. Does it require a specific type of parent star? Is there a perfect recipe of spin, mass, and internal composition? Each new magnetar we discover adds a piece to this puzzle. Studying them is more than cataloging stellar oddities. Magnetars are natural laboratories for physics under conditions we could never hope to create on Earth. Their surfaces are a bizarre landscape where the magnetic field is so strong it can catalyze chemical reactions, potentially creating a form of nuclear pasta, dense strands of atomic material. They teach us about the behavior of matter at the very edge of existence, where protons and electrons are crushed together and magnetism becomes the dominant force in the universe. In their brief, violent lives, they probe the absolute limits of what is physically possible. The unimaginable magnetic violence of a distant star is matched by a profound quiet much closer to home, a silence in the expected cosmic chatter of our own solar system's frozen frontier. Beyond the orbit of Neptune lies the Kuiper Belt, a vast donut-shaped realm of icy remnants left over from the solar system's formation. It is home to dwarf planets like Pluto and countless smaller bodies, a cosmic junkyard that should, according to our best models, grow steadily denser with objects the farther out you look. But it does not. Instead, astronomers have mapped a startling and abrupt boundary, a cliff edge in space where the population of these icy objects suddenly and inexplicably plummets. This is the Kuiper Belt Cliff. Based on our understanding of how the solar system coalesced, there should be a smoothly increasing number of small, icy bodies at distances around 50 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun. Yet, detailed surveys, like those conducted by the Subaru telescope in Hawaii, reveal a dramatic scarcity. It is as if someone drew a line in the cosmic sand and declared that beyond this point the icy debris simply stops. The drop-off is too sharp, too clean to be a simple fluke of observation or a natural outcome of the solar system's birth. Something has actively sculpted this edge, clearing out a region that should be teeming with frozen fossils. The most compelling explanation points to the gravitational hand of a hidden giant. Astronomers hypothesize that a yet undiscovered planet, perhaps 5 to 10 times the mass of Earth, orbits the Sun far beyond the Kuiper belt. This hypothetical world, often called Planet 9 or Planet X, would move on a long, elliptical path that takes it hundreds of astronomical units from the Sun. As it makes its multi-thousand-year journey, its immense gravity would act like a cosmic shepherd, gravitationally nudging the orbits of smaller Kuiper belt objects. Over billions of years, this influence could have shepherded some objects into clustered, tilted orbits we have already detected, while violently ejecting others from the solar system entirely, carving out that observed cliff in the population. The Kuiper belt cliff is not direct proof, but it is a powerful shadow, a negative space in the celestial census that points to a massive, unseen presence. The hunt for this phantom planet is now a meticulous astronomical detective story. Researchers are scanning the coldest, darkest reaches of our solar system, looking for a single, faint point of reflected sunlight moving slowly against the backdrop of fixed stars. It is a needle in a haystack the size of a galaxy, but the gravitational clues it has left behind, etched into the strange orbits of distant objects and this stark population drop, make the search irresistible. Finding it would be more than just adding a new planet to our textbooks. It would rewrite the story of our solar system's formation and its dynamic history, revealing a hidden architect that has been silently shaping our cosmic neighborhood for eons. That hidden architect shaping our solar system's edge operates on a local scale, but the universe carves out absences of truly incomprehensible size. In the constellation of Boötes, the herdsman, lies a region of space so profoundly empty it has earned the name the Great Nothing, the Boötes Void. Imagine a sphere of nothingness so vast you could fit thousands of galaxies like our Milky Way inside it, and then leave it almost completely dark. This void is not a perfect vacuum, but a cosmic desert approximately 330 million light-years across where the expected population of galaxies has simply failed to appear. While our local universe is structured like a glittering web with dense clusters and filaments of galaxies, the Boötes Void is a corresponding hole in that web, a bubble of startling emptiness. The mystery is not that voids exist, they are a natural part of the cosmic structure. Gravity pulls matter into filaments and clusters, leaving behind less dense regions. But the Boötes Void is an outlier, a supervoid of such extreme size that it strains our standard models of how the universe organizes itself. Based on the distribution of matter we see in the cosmic microwave background and the predictable action of gravity over billions of years, we would expect a region this large to contain at least several thousand galaxies. Instead, astronomers have catalogued only a few dozen, scattered like lonely islands in an ocean of dark. It is as if someone took a cookie cutter 300 million light-years wide and removed almost all the stars. How does such an immense nothing come to be? One theory suggests it is not a single void, but the result of several smaller voids merging together over cosmic time, like soap bubbles combining to form one gigantic cavity. Another, more speculative idea involves dark energy. Could the repulsive force accelerating the universe's expansion have acted more strongly in this specific region long ago, pushing matter out and preventing galaxies from ever forming? While intriguing, this remains a fringe hypothesis without solid evidence. The prevailing view is still that the void is a rare but natural statistical fluctuation in the primordial soup of the universe, a place where, by sheer chance, the seeds for galaxy formation were exceptionally scarce. Yet, its very existence is a crucial reminder. The Boötes void challenges the cosmological principle that the universe is smooth and uniform on the largest scales. Instead, it showcases a cosmos that is lumpy and unpredictable, capable of producing structures of both immense density and staggering emptiness. It forces us to ask if our corner of the universe is truly typical, or if we simply live in a relatively crowded neighborhood, blind to the vast deserts that make up most of the cosmic landscape. This great nothing is not an absence of mystery, but a presence defined by it, a silent, spherical question mark hanging in the dark. Even the silent, airless moon has its moments of strange and fleeting light. For centuries, sharp-eyed observers have documented brief, unexplained glimmers and obscurations on its familiar face. These are lunar transient phenomena, or LTP, flashes of light, patches of color, or sudden hazes that appear for minutes or even hours before vanishing without a trace. The records go back to at least 1787, when the astronomer Sir William Herschel, the man who discovered Uranus, reported seeing red glowing spots on the dark part of the moon, which he believed to be volcanic eruptions. Over the following 200 years, hundreds of similar reports piled up from both amateur and professional astronomers. They described everything from pinpoint flashes to diffuse purple hazes, from brightening of crater walls to sudden, localized fogs that would blur surface features before dissipating. The moon, a world without an atmosphere, without weather, and thought to be geologically dead for billions of years, was apparently winking at us. Modern science has taken up the challenge of explaining these ghostly events, but capturing one is like trying to photograph a lightning bug in a distant field with a telescope. The events are random, brief, and notoriously difficult to verify. Is it a trick of the eye, a flaw in the telescope, or a genuine lunar mystery? To find out, projects have been launched to monitor the moon continuously with automated telescopes, hoping to catch these phantoms in the act. When they do, the hunt for a cause begins. The leading natural explanations are as intriguing as the lights themselves. One strong candidate is outgassing. The moon's interior may still hold traces of radioactive elements that slowly decay, producing heat. This heat could occasionally release trapped gases like radon from deep below. When these gases vent to the surface and are exposed to sunlight, they might briefly glow or scatter light, creating a visible haze or bright spot. Another idea points to electrostatic activity. The moon's surface is constantly bombarded by solar wind and ultraviolet light, which can give the fine lunar dust an electric charge. This charged dust might occasionally levitate above the surface, creating a temporary, shimmering cloud that could obscure details or catch the sun at a certain angle. And of course, there are meteorite impacts. A small rock striking the moon at tens of thousands of miles per hour releases a tremendous flash of heat and light, an explanation that certainly accounts for the briefest, most brilliant events. Yet for every event that might be explained by gas or dust or impacts, there remains a stubborn catalogue of observations that do not fit neatly. Some reported glows last too long. Some color changes are too vivid. Some obscurations cover areas too large for a simple impact plume. This enduring uncertainty is what keeps the mystery alive. It adds a thrilling element of dynamism to a world we have walked on and mapped in exquisite detail. Our robotic orbiters have photographed nearly every square inch, yet they have not solved the puzzle of these transient whispers. They remind us that the moon is not a static museum piece, but a world with subtle, ongoing processes we are only beginning to understand. Every unexplained flash is a question, a suggestion that even our closest celestial neighbor still holds onto a few of its secrets, waiting for the right moment to reveal them. That silent, watchful moon offers no answers to the most pressing measurement crisis in all of modern cosmology. For over a century, we have known the universe is expanding, but now the precise rate of that expansion has become a source of profound disagreement. This is the Hubble tension, a stubborn discrepancy between two of our most trusted cosmic measuring tapes. and it threatens to unravel our standard model of the cosmos. The problem is not a small error, but a growing chasm between how fast we think the universe was expanding in its infancy and how fast we see it expanding right now in our cosmic neighborhood. Both measurements are made with exquisite precision, and both are almost certainly correct, yet they cannot both be true under our current understanding of physics. It is like using two perfectly calibrated rulers to measure the same table and getting two different, undeniable answers. The first ruler looks back to the very beginning. It uses the afterglow of the Big Bang, the cosmic microwave background, as a frozen snapshot of the infant universe when it was just 380,000 years old. By mapping the tiny temperature fluctuations in this ancient light, scientists can deduce the universe's ingredients, the amounts of ordinary matter, and dark energy. Plugging these numbers into our standard model of cosmology, we can run the cosmic film forward to predict what the expansion rate should be today. This method gives us a Hubble constant of about 67 kilometers per second per megaparsec. In simpler terms, for every 3.26 million light-years you look out into space, galaxies appear to be receding from us 67 kilometers per second faster. The second ruler measures the present-day universe directly. It relies on a cosmic distance ladder, a series of interconnected steps to gauge how far away things are. The first crucial rung is built with Cepheid variable stars. These are stars that pulse with a regular rhythm, and their pulse period is directly tied to their true brightness. By finding Cepheids in nearby galaxies, we can measure their apparent brightness, compare it to their known true brightness, and calculate an accurate distance. We then use these galaxies as anchors to calibrate the next rung, Type 1, a supernova. These stellar explosions are the universe's ultimate standard candles, always shining with the same peak brightness. Once calibrated by Cepheids, we can use these supernovae to measure distances to galaxies far across the cosmos. By then measuring how much the light from these supernovae is stretched or redshifted, we can calculate how fast the universe is expanding now. This meticulous step-by-step process yields a different number, about 73 kilometers per second per megaparsec. The gap between 67 and 73 seems small, but in the world of precision cosmology, it is a yawning canyon. As telescopes like Hubble and now Webb have collected more and better data, the error bars on each measurement have shrunk to tiny slivers. The discrepancy has not gone away, it has solidified. The two numbers are now separated by a statistical gulf so wide that the chance this is a simple mistake is less than 1 in a million. The universe, according to our best tools, is expanding significantly faster today than our model of its early history predicts it should be. This is the tension, a direct conflict between our story of the past and our observation of the present. Such a fundamental mismatch suggests our standard cosmological model, lambda cold dark matter, is incomplete. It has been wildly successful at explaining the large-scale structure of the cosmos, but the Hubble tension is a crack in its foundation. Cosmologists are now exploring radical fixes that sound like science fiction but are deadly serious proposals. One leading idea is early dark energy. This posits that a strange, repulsive form of dark energy, distinct from the one causing today's acceleration, briefly surged in the universe's first few 100,000 years. This extra push would have subtly altered the conditions imprinted on the cosmic microwave background, changing the predicted expansion rate for today to match what we actually see. Another possibility involves exotic neutrinos, ghostly particles that could have interacted in unexpected ways in the primordial soup, altering its recipe. There are even suggestions that dark matter might not be completely cold and passive, but have a tiny amount of intrinsic motion that would affect how structures formed. The Hubble tension is more than an academic puzzle. It is a direct challenge to our cosmic biography. It forces us to question if we have missed a crucial chapter in the universe's first moments, or if a fundamental ingredient in our cosmic recipe is wrong. Every new observation, every more precise measurement tightens the knot. Resolving it will not be a minor adjustment, but a potential revolution in our understanding of time, space, and the very forces that have shaped everything we see. This journey has taken us from a single, unexplained radio signal to the very fate of the cosmos itself. We have listened to the void and heard a shout that never repeated. We have felt the pull of invisible matter and the push of a phantom energy, forces that sculpt the universe in the dark. We have watched stars flicker under impossible shadows and spacecraft drift on unseen currents. We have stood at the edge of a solar system abruptly cut short and peered into a spherical void of staggering nothingness, and we have measured the very expansion of reality, only to find two conflicting answers staring back at us. Each of these 25 phenomena is a locked door at the frontier of human understanding. They are not failures of science, but its very purpose. Every unexplained signal, every anomalous motion, every defiant measurement is a signpost pointing toward a deeper truth we have yet to grasp. They remind us that our maps of the cosmos are still filled with blank spaces labeled "Here be dragons," and that the universe is perpetually stranger, more complex, and more wonderfully bizarre than our boldest imaginations. It is this endless mystery that fuels our curiosity and drives us to build better telescopes, craft new theories, and keep asking the next great question. So as we look up at the night sky, we are not looking at a solved puzzle, but at an infinite story still being written. Which of these cosmic enigmas captured your imagination the most? Was it the eerie perfection of Saturn's hexagon, or the chilling solitude promised by dark energy? Share your thoughts in the comments below. If you crave more journeys to the edges of knowledge, be sure to subscribe. Until next time, keep wondering and keep looking up.